Okay, so I'm going to run through the lecture that many of you are missing today because of the student class meetings, just that way that no one gets behind, because measurement and SigFigs and all of that is very, very important, and it's stuff that's going to follow us for every unit that we do the whole year long. So those of you that did have to miss today, don't freak out. This will be your lecture. It will be the same as what the folks that stayed in class got. So we're going to run through this real quick. So first of all measurements require a numerical value and a unit. Numbers without units are absolutely meaningless. If a unit is given to you in the course of a problem, a unit should be given as part of your answer. If you don't give units, I don't know if you're talking about 4 cups, 4 grams, 4 liters, 4 pink fluffy bunnies. I have no way of knowing. So make sure that you include units when you are given units. Points are deducted if you don't include a unit, meaning if you are doing a worksheet that has 25 problems and you give me 25 perfectly beautiful correct answers, but you don't include any units, -1 per unit you don't have, that's a 75, and you did everything right. So you need to make sure that you're watching and you're being very vigilant about having units. Right? There are 2 main systems of measurement: the English system, which is what you grow up using in elementary school, feet, inches, pounds, gallons, and then the metric system, what we use in science, grams, meters, and liters. And then the metric system has been kind of streamlined for use worldwide in what we call the System International, the system of international units, where we have a series of base units and then we use metric prefixes. So you may have remembered from biology, depending on who you had, this stair step line, kilo, hecto, deca, your base unit, deci, centi, I left one out, milli. Those are all your prefixes. Anything that is above the base here, these are very large. Anything that is below the base, these are very small. And you can use any of these prefixes along with a base unit to denote whether you're talking about a big measurement or a small measurement. Our base units, for mass, we use the gram, but also the kilogram is an acceptable base unit. Because grams are so small and most things that you weigh are relatively large, kilogram, even though it does have a prefix, is accepted as a base. Length is the meter, so a large amount of length would be a kilometer, a small would be a millimeter. Time is in seconds, and temperature is in Kelvin. Kelvin is the absolute temperature scale. And we also use Celsius, but Kelvin, especially when we get into things like gas laws, is what we're going to be using. Mass versus weight. So mass is the amount of matter in an object, whereas weight is how that mass is affected by gravity. The mass that makes up anything does not ever change, but the weight will vary based on your position on this planet. Just for example, if you were to go to the moon, obviously you know that gravity is less. So if the force of gravity is less, then that gravity times your mass is going to equal a lower weight. All right. Derived units is where we take a combination of base units. So for example, when you are measuring the volume of a solid object, length times width times height, those are all measurements of length in meters. So meters times meters times meters gives us this cubic meter. If we were talking about a very small object, it could be centimeters cubed or millimeters cubed as well. All right. Measurement uncertainty. So this is what occurs when you are taking measurements on an actual measuring device that is not digital. So when you are looking, for example, on a graduated cylinder or on a ruler, right, there's measurements that you know for sure because they're marked, and then there's measurements that are in between the marks that you have to estimate. So the exact digits are the ones that are marked. So in this particular example over here, we know that we're past 7. And it looks like our meniscus is past the 7 and also past the first mark, but a little bit between the first mark and the second mark. So we would say this is 7.1, and then we'd have to make an estimation of where it is in between. So the exact measurements would be the 7 and the 0.1. We know those for sure because they are marked. The uncertain digits are the ones that we then have to estimate. It's important when you are estimating your digits to know the scale of the tool that's being used. So for example, here we have two pictures of two graduated cylinders. You have a 100 ml graduated cylinder where each mark is 1 milliliter. You have a 10 ml graduated cylinder where each mark is 0.1. So here, when I'm estimating one place past what is marked, I would be estimating a 10th position. Here, where I'm estimating one place past what is marked, I would be estimating a 100th position. So you have to know what the scale is of the measuring tool to know what position of a number you are then estimating. Okay. Measurement uncertainty continues with the discussion of precision and accuracy. So precision is how close a set of measurements are to each other. In order to have precision, you have to have multiple trials of the same experiment. So for example, if I was asking you to determine the volume of a quantity of water, you would have to do that same quantity multiple times in order to say that you have precision. If you only do it once, you cannot say that you have precision. You could potentially have accuracy, closeness of that measurement to the accepted value, but you can't have precision. Precision has to have repetition. So here we have accuracy, reasonably close to the target. We have precision, all of our measurements grouped together. We have precision and accuracy, which is A1, what you want to strive for. And then we have just all over the place, neither precise nor accurate. Okay. All right, then we're going to go into SigFigs and scientific notation, and this is really the meat of our information here. I'm just going to slide a piece of paper under here real quick. So every time you do any sort of calculation in this class, you have to, as I say, respect the SigFigs. You got to make sure that you are reporting your answer to the appropriate number of SigFigs, because that tells me how accurate your answer is able to be. And then scientific notation is just a good way for us to report very, very large or very, very small numbers without having to write out a whole bunch of zeros. All right, so let's talk about our rules for SigFigs. So digits that carry meaning contribute to the precision or accuracy of a measurement. And there are rules for SigFigs based on what you have in terms of the measurements that are given. So our rules is anything that is not a zero is automatically significant. Does not matter what position those numbers are in, any place that they are located is a significant digit. Zeros that come in between two non-zero digits are always significant. I call these the sandwich zeros, right? 102, the zero is sandwiched in between, like bread, meat, right? It's going to count because it's in between two non-zero digits. Same thing here with 2005. Same thing here with 50,009. You can't just take those numbers out of the middle. They count. So zeros between two non-zero digits automatically count. Right? Leading zeros are never significant. So these zeros here that are simply there to space the decimal away from the first non-zero digit are not significant. They're placeholders. A good way to look at this is if I were to put this number into scientific notation, they wouldn't be there. They're only there to hold the space. Okay. In a number with a decimal point, trailing zeros are significant. They add to precision. So say, for example, this 5.400, if this was a weight we were taking on a digital balance, tells me that this value is known to the thousandth position. That is a very good, very expensive, by the way, scale. So if I have a decimal, those trailing zeros are significant. If I don't have a decimal, then trailing zeros are not significant. For example, this 400 would only be one significant digit, whereas if I had 400 decimal, I would have 3. The decimal adds the significance, whereas without it, this does not have it. So let's get some practice counting our significant digits. All right, so on your notes, in the spaces I've told you to leave, if you'll write those down, may want to pause me, write them down, and then we're going to go through how many significant digits are in each one and why. Pause me, write them down. Okay, I'm going to assume that you paused me and you wrote it down. All right, so in the first one, 1,201. So I've got the 1, the 2, and the 1 automatically count because they're not zeros. And then the 0 in between is sandwiched. So this would have 4. Okay. For the next one, 0.00347. These zeros in front are just spacing our decimal. They are leading zeros. Therefore, if I were to put that into scientific notation, they wouldn't count. So this one, we'd start counting at the 3. 347 would only have 3. Okay. 594.001. We've got the 5, the 9, the 4, the 1 all count automatically because they're not zeros. Then these two zeros are sandwiched in between two non-zero digits. So we would have 6. Okay. 13.100. The 1, the 3, the 1 all automatically count because they're non-zeros. These two zeros are following a significant digit following a decimal, so they absolutely count. And we have 5. All right, 100, no decimal, only one significant digit, just the 1. 1,001, we've got the 1, 2 sandwich zeros, and a 1, so that's going to be 4. 15.000, the decimal makes them significant, so we have 5. And then 500 with the decimal makes those zeros significant, so we have 3. Okay. The first step to any problem is doing the number of significant digits in your measurement. So you need to be able to identify these really quickly. And then once you get good at it, it becomes really, really easy. All right, so let's go on to the next thing. In calculations. So in calculations, the measurement with the smallest number of SigFigs rules and tells me how many SigFigs I can have in my answer. So, for example, in this problem, 4.30 meters, 5.077 meters, and 0.10 meters. How many SigFigs does each measurement have? So in the first one, 1, 2, this is following a following a decimal. This is 3 SigFigs. 1 sandwich, 2, 3, 4, and 0.10 would be 2. So that means that my least number of SigFigs is 2. So this one is going to determine how many I can have. My answer is going to have 2 SigFigs. So when I type this in my calculator, I come out to 2.18311. But if I make that to 2 SigFigs, 1, 2, this 8 is going to definitely round over. I'm going to have 2.2. And then meters times meters times meters is meters cubed. Now, let's kind of pause here for a second and talk about rounding. When I'm rounding, I look one place past the number of significant digits I have and one place only. So if I have 4 significant digits, I look at the 5th number. If the 5th number rounds, I round. If it doesn't, I don't. We don't do this, well, this rounds that, and that rounds that, and that rounds that. We don't do any of that. If this was a 4, it wouldn't round. The answer would have been 2.1. 5 or higher rounds up, 4 or lower stays the same. Okay, no downstream rounding. All right, so let's do a couple more examples of multiplication and division, and then we will get addition and subtraction. All right, so in our first example here, we said the least number of SigFigs rules. So 291 has 3 SigFigs. 0.009, remember these are leading, so they wouldn't count. We have 1. So when I put this into my calculator, let me clear that off. 291 times 0.009 comes up to 2.619. But I can only have 1 SigFig. So I look at that first digit. Does the 6 round the 2? 6 rounds the 2 up. My answer is 3. No measurements were given as terms of a unit, so 3 is just my answer. All right, let's look at the next one. All right, so we've got 55, 2 non-zero digits, so 2 SigFigs. We see this one again from the one of previous. And then this one, 60 point. So the decimal point here is going to make this significant. So I'm going to have 2. So when I put this into my calculator, 55 times 0.009 times 60 comes out to be 29.7. I can only have one sig fig. So the 9 rounds this up, but is it 3? That doesn't make sense, right? If the answer is 29.7, 3 is not going to work. Always think about money in situations like this, right? If I owed you $30, right? 29.7, $29.70, you'd be pretty irritated if I was like, okay, here's $3, right? You'd be a lot less irritated if I was like, here's $30. You've got to have a number that represents the value of your answer. 3 does not represent the value that is 29.7. 30 does, and that's still only one sig fig because there's no decimal. The other way you could write it, if this is like wigging you out because you're writing 2 things down and it's only one sig fig, 3 times 10 to the first, put it in scientific notation. Either one of those is correct, but you got to think about money. All right, let's look at the next one. 407, 36.2. So 407 is 3 sig figs. 36.2 is also 3 sig figs. So let's put that one into our calculator. Oops, 36.2. And that comes out to be 11.24309. All right, I can have 3 sig figs. So 1, 2, 3. Does the 4 round the 2? Well, we said 4 and lower, we just drop. So drop that. 11.2 is our answer here. Okay. All right, we come down to our next one. 8,020. So for 8,020, the 8, the 0, and the 2 all count. This 0 counts because it's in between, but this one does not. There's not a decimal. If I put it in scientific notation, it wouldn't be there, so we just have 3. And then this one's easy because they're all non-zero. We've got 4. So 8020, oops, move it so y'all can see. 8020 divided by 3.477 gives me 2,306.586. All right, so again, I need 3 sig figs. 1, 2, 3, the 6 rounds. Now, is my answer 231? Does 231 accurately represent the value that is 2,306? Think about money. If I owed you $2,306, you'd be pretty hacked off if I gave you $231. But you'd be okay if I gave you $2,310. 3 sig figs, the 0 doesn't count for the significant figures. All right, and our last one here. We have a number in scientific notation, 2 times 10 to the minus second times 8.33. So you can leave this in scientific notation, or you could take it out. The good thing about scientific notation is it only shows me the digits that are significant. So this only has one significant digit. 8.33 has 3. So when I multiply this out, 2 times 10 to the minus second times 8.33, I get 0.1666. I can only have one significant digit. So 1 in the 6 rounds, so 0.2. Okay. All right, so those are your multiplication division examples. Let's go look at addition and subtraction notes. All right, so for addition and subtraction, different rules. The number of significant digits depends on the number with the least number of decimal places, which means overall sig figs does not matter. We only care about the number of decimal places. So let's look at our example. How many decimal places are in this number? Well, just 1, right? That one there, so 1. How many decimal places are in this number? Well, 0, it's a whole number. How many decimal places are in this number? All right, we've got 3. So which one will determine the number of decimal places? The one with the least number of decimal places. All right, so the whole number is going to be the one with the least number of decimal places. So how many decimal places will my answer have? None, because it's got to be rounded to a whole number. So I add them up. This is what I get when I add them up. And I'm just going to round if necessary. So 9 obviously is going to round this up. 2204 is my answer. We carry all the extra digits. The very last thing we do is do our SigFigs. Okay, so let's do some examples with with addition and subtraction now. All right, so addition and subtraction. Again, the measurement with the least number of decimal places is going to be the one that determines the number of decimal places in our answer. Overall SigFigs does not matter. So in our first example, we have 4 decimal places and 3 decimal places. So our answer is going to have 3 decimal places. 52.2754 plus 5.151 gives me 57.4264. I can have 3 decimal places. So I'm going to start counting after the decimal because that's what I'm worried about. 1, 2, 3. Does the 4 round the 6? Nope, drop it. So my answer is 57.426. All right. For the next one, 64.8 plus 5.2. So what? 1 decimal place, 1 decimal place. 70. Was that my answer? Well, yeah, 64.8 plus 5.2 sure does equal 70, but you would lose the SigFig point here if you don't include a 0.0. Why? Because each of these has a decimal place. If you wrote this out like you did when you were in like 4th grade, 64.8 and 5.2, and 8 plus 2 is 10, decimal carry the 1, 4, 5, 1, 10, 7, you see it right there, but your calculator takes it away. Okay, got to be smarter than your calculator. If you have one and you have one, you can always add a 0.0, right? That's always allowed. All right, next one. 61.3454, that has 4. 25.1 has 1, so my answer can have 1. 61.3454 minus 25.1 gives me 36.2454. So 1 decimal place. 1, does the 4 round? Nope. 36.2. Okay. All right. The last thing that we need to look at is some examples with scientific notation. So in scientific notation, we are going to have a number between 1 and 9, all right, and a power of 10 with an exponent. If the number is greater than 1, my power of 10 is going to be positive. If my number is less than 1, my power of 10 is going to be negative. The easiest way to look at these is do it like 3rd grade style with some froggy hops. All right, so I'm going to zoom in a little bit. I have to get my decimal to the point where the number is between 1 and 9, and then I have an exponent. So here, this is smaller than 1, which means my power of 10 is going to be negative, to the tune of, hop your decimal, 1, 2, 3. 3.45 times 10 to the minus 3rd. 3.45 times 10 to the minus 3rd. For this one, this is definitely greater than 1. My decimal here is invisible behind the 0, so I'm going to hop it the other way. 1, 2, 3, 4, 5, 6, 7. 9.4 times 10 to the 7. Okay. Here, we're going to go the other way. This is less than 1, so my exponent is going to be negative. 1, 2, 3, 4, 5, 6. 7.6 times 10 to the minus 6th. All right. 82.103. I got to make it between 1 and 9. Scoot it over 1. 8.2103 times 10 to the 1st. 9,740. 1, 2, 3. 9.74 times 10 to the 3rd. Why didn't I include that last 0? No decimal means it's not significant. All right, for these bottom ones, we're taking it out of scientific notation. So 6.7012 times 10 to the 1st, that means that because this is positive, it's going to be bigger. So we're going to take it out and go 1 to the right, 67.012. All right. 7.5 times 10 to the minus fifth. Negative exponent means this is going to be a small value. We're going to hop it out 5 places to the left. 1, 2, 3, 4, 5. Fill in with zeros. And I like to put a 0 in front of my decimal, make a nice bold decimal. You don't have to. You can just have the decimal in front, but you got to make sure it's a nice bold decimal that people can see. So 0.4075. All right. And our last one, 9.5048 times 10 to the second, 2 places to the right, 950.48. Okay, you should now have enough information to be able to do your homework. If you get stuck, feel free to message me.